Keep an eye out for Steve. If when he comes, let me know. So anyway, that way you'll get all of us. So as I was explaining before, it's a pleasure to be here. Thank you very much for the invitation. There's been a lot of interest lately amongst the particle physicists, the field theorists, about the hierarchy problem. And this has gotten more severe because, and that's the question of why the Higgs is so light. And that's gotten more severe because the explanation everybody assumed was that we would find weak scale supersymmetry at the LHC. And we haven't. And it's already beyond the point that we know that the scale now of SUSY breaking is at least high enough that that supersymmetry, weak scale SUSY, cannot be the only answer to the hierarchy problem. There must be other contributing factors, but people are now beginning to think that maybe we need to reimagine other ways of approaching hierarchy problems. And I was actually at a workshop that was organized at CERN in early January, and it was focused on, actually my collaborator Steve Abel was one of the ones organizing it, on ideas, exotic ideas for hierarchy problems, things that people had not thought about, things that are not supersymmetry, where for every boson there's a fermion at the same mass, and you pair them up and go all the way to infinity. And so the ideas that people have been talking about, especially in the field theory community, are UV-IR mixing, the roles of effective field theories. Maybe the idea of an effective field theory is leading us astray in some way. Maybe there are hidden cancellations. Sometimes people call these magic zeros. And so the attitude that Steve and I, and also Luca, say hi. Luca is also a collaborator on this second paper, are that maybe we should think more about what string theory is telling us, because string theory has UV-IR mixing, it has effective field theories, it has hidden cancellations. And maybe we should take string theory very seriously and use string theory as a guide to ask what happens in field theory. So this talk is going to be maybe a little bit weird because I'm going to try to be going back and forth between field theory ideas and string theory ideas. And this audience, I think, is very knowledgeable about string theory, but other audiences are not knowledgeable about string theory at all. So what I'm going to try to do is bring along the field theory ideas and the string theory ideas simultaneously. So I'm going to introduce everything that you need. You don't need to have any prior knowledge for this talk. So the basic idea is to explain this circle. So let me say that this is work done in two papers, one long paper with Steve Abel, who will join us soon in about a half an hour, I think, and a second, more recent paper with Steve and also with Luca, who's here. And this first paper discusses the Higgs mass. The second paper discusses the gauge couplings and the running of the gauge couplings using the techniques that were developed in the first paper mostly, but then new techniques were also needed here. And so I'm going to try to summarize all of this together. And a lot of this is based on a long line of earlier papers that I was working on, about 30 years ago, and which have sort of come into relevance again, which is always nice to see. But that's what we're going to try to do. And so I'm going to introduce everything as we go along. And if you're knowledgeable about string theory, you're going to recognize it at a few places. Oh, that's what I'm doing. But hang on, because it's going to be done in ways that you have not seen before, probably. So the idea is to explore the circle of ideas in field theory that people are now talking about for hierarchy problems, or let's call it exotic approaches to naturalness. And the first one, of course, is this whole notion of hierarchy problems are really about the existence and stability of widely separated energy scales with respect to quantum corrections. Quantum corrections destabilize the separations. That's the problem. And so this is about relations between UV and IR physics. So it's really natural to explore these ideas in a context in which these interact and mix and are related to each other. Seems very natural that if you want to talk about hierarchy problems, you should be thinking about UV and IR and connections between those. So the first thing we're going to be focusing on is UV-IR mixing and the symmetries that do that. That's going to be leading us to string theory. The second idea is related because these UVIR symmetries involve physics at all scales, you're not going to see them if you're only restricted to low energy physics, which is what we as observers, we can only see low energy physics. In that case, whatever magic the UVIR mixing is doing for us would appear to us to just be some sort of hidden cancellations, whatever dangerous operators we would imagine might be there. Maybe UVIR mixing is curing that disease, but to us at low energies, all we would see is that the coefficients of these operators are magically zero. It would look like maybe supertrace constraints did that, but we don't have supersymmetry. So this is the idea that maybe there are going to be some sort of finiteness through hidden cancellations. The next observation that comes if you walk down this road too far is that you realize that because these cancellations are the results of and protected by these mixed symmetries, if there are any, they would rely on physics conspiracies, really. It would seem like conspiracies, but physics between at all scales simultaneously. It's UV, it's IR, it's all of it mixed together. And so these theories would have to have a rich physics populating all scales, including infinite towers of states. So that's really the third thing, that we're going to really be talking about theories with infinite towers of states and what that can do, not just finite, but infinite. And then the fourth idea is that if these theories have UVIR mixing and they achieve finiteness through conspiracies involving physics at all scales simultaneously, to what extent then can you even talk about a low energy EFT description? Are we correct to think about effective field theories or not? In string theory, this is a very important question. So is it possible to extract an EFT from such a theory that has UVIR mixing, like string theory does? What role would an EFT play, and how could it really be interpreted in a self-consistent way? So this is the circle of ideas, really, that we're going to be talking about in this paper, and this is in this talk. And there are, you see, they're not necessarily string theory. But I think it's important, if we're going to talk about these kinds of theories, that we study them, these ideas, in models which are UV complete, in theories which are UV complete. And the one that we know is string theory. And string theory indeed gives rise to all of these features: hidden cancellations, infinite towers of states. How can we get EFTs from string theories? And also, of course, UVIR mixing is a critical component of string theory. So really what this talk is about is how these ideas, which are field theory, come into and are realized in string theory, and what do we learn from that realization. So I'm going to start in this talk by discussing these ideas in complete generality, really in a field theory way. Always I'm going to be kind of moving back and forth between field theory and eventually string theory. And then we're going to illustrate the power of these ideas by actually calculating the Higgs mass in string theory. And I will discuss at the end of the talk how the gauge coupling running looks very similar to what we get from the Higgs mass, all these amazing features. But we're going to do this in a way that keeps track of the full UVIR mixed string symmetries and the complete towers of states. We're not going to integrate anything out. And this is very important to stress, because previous attempts to talk about these ideas, things like Higgs masses, running of gauge couplings. I myself, 30 years ago, wrote a Physics Reports article on the running of gauge couplings in string theory. Well, we did everything that we normally do. You integrate out all these heavy states. We're not going to do that here. We really want to pay attention to the UV-IR mixed symmetries, because this is what's unique about string theory. We should not lose this when we try to answer these difficult questions. So I'm going to start the story by looking at the one-loop Coleman-Weinberg effective potential in field theory. This is field theory. So this is a standard result in Peskin and Schroeder, any field theory textbook that you like. And this is not going to be a highly, highly technical talk. I really want to focus on the ideas, but it will help just to go down one or two pages of some algebraic results, just so you see how this works. So this is the standard result. This is the cosmological constant, or the one-loop effective potential, the one-loop vacuum energy. It's the 0.1 loop function. And what it is you sum over all the states in the spectrum. That's what they are. -1 if it's a fermion, and +1 if it's a boson. So -1 to the fermion number of states at that level. So the total number here is the number of bosons minus the number of fermions, which of course would be 0 for supersymmetry, but we're not going to be in supersymmetric theories. We are not avoiding supersymmetry. It's part of everything, but we don't want to assume it either. That's the whole point. The world is not supersymmetric. And then for each of these states, that has a mass at every level n. Here, the mass is here. You integrate over all the momenta in the loop. That's what you get. This is the standard field theory result. Now, it turns out that there's another formulation for field theory that most people don't really know, and we should know it, because this is the way to connect field theory to string theory. And it's called the Schwinger world line formalism. And the basic idea, it's purely field theory, not doing string theory. It's just that this becomes the road to talking about string theory. It's purely field theoretic. The idea is, instead of calculating normal amplitudes, you calculate an amplitude with a t, a restriction on this total time. Basically, you calculate the amplitude for the particle to move from, say, x to y within a fixed proper time t. And that's called the Schwinger proper time. So in this sense, t is like the total length of the world line around the bubble. This is not something you normally pay attention to in the standard formulation of field theory. But you can do this. And then what you say is that the total propagator is the integral of this amplitude over all of those t's, all those Schwinger proper times. So this becomes a way of writing field theory amplitudes as integrals over a Schwinger proper time. Algebraically, it amounts to just turning this log into something that looks a little bit different, like a log. You're taking that log of any x, and you're just writing it in terms of a Schwinger proper time, an integral t. And so if you do that here, to write the Schwinger proper time representation for this amplitude, the log is p squared plus m squared. So now you just have the same thing. Here it is, the integral over t, and there's the p squared plus m squared up there. And now you could just manipulate. This is the most technical slide I'm ever going to have. You do the p integrations. It's no big deal. You get an angular factor, and there's more powers of t that come downstairs. Here they are. It depends on how many space-time dimensions we're in. There's the sum over states. The Schwinger proper time, now we look at it and we see, well, it's got a mass dimension, because if it's up here in the exponential, it's got a mass dimension -2. And I don't like to do that. Let me pull out all the masses. So I want to introduce a dimensionless Schwinger proper time. So I'm going to change this. I'm going to pull out an overall mass scale and then call my dimensionless Schwinger proper time T2. Why am I calling it T2? Well, those of you can guess who already know. If not, I'm just going to call it T2, and the reason will be clear in a minute. But now T2 is dimensionless. So I do that. I pull out my mu, my overall unknown arbitrary scale. Here it is. It turns out that everything here now becomes dimensionless. This is, any mass is expressed in units of mu squared, and we have an overall mu squared in the front. So mu now sets the scale for this quantity lambda, so it's the overall size of everything. And you look at this thing and you say, well, that looks like a partition function. In particular, it looks like a thermodynamic partition. Here's your Boltzmann factor. It depends on how much energy there is. E to the minus T2 looks like a temperature. It's like a Boltzmann factor. Number of states. The only difference is it's actually got a -1 to the f. So it's a graded partition function. It's not like a thermodynamic one where everything would be a plus. But otherwise, we're going to call this the partition function, z of T2. And so sum over all states in the spectrum. And so what we've now done is write the one loop effective potential as an integral with some factors over Schwinger proper time of a partition function. So here it is again. That's all we're saying. This is a simpler, more beautiful way to write that amplitude. Every theory has a partition function. It depends on that T2, and you write it this way. And it's an integral over a line from T2 goes to 0 to infinity. The next step, I'm just going to, and this is, of course, building towards string theory. Okay, again, those of you who recognize what I'm doing, no secret here. I'm going to introduce a dummy variable T1. And it's just a dummy variable. Nothing else is going to depend on T1. So I integrate from -1/2 to plus. This is another way of saying 1. Everything in this red box is just 1. And I've inserted it. And so what I'm doing, though, is now I can integrate over T1 from -1/2 to +1/2 and T2 from 0 to infinity. I'm basically puffing this out. And so now my integral, if I call this the T1 direction and this is the T2, of course, there's no physics in this T1 direction. Nothing depends on T1. It does depend on T2, but nothing depends on T1. But I can still do this, and then I would call this thing the strip. It goes from -1/2 to +1/2, from 0 up to infinity. And so the prescription is, in field theory, I integrate over the strip. Here's my measure, and here's the partition function. Okay? Very clear. There's the summary. In ordinary quantum field theory, I know that I should integrate over the strip, of the partition function, and there's the strip. Yeah, questions. Always interrupt.
Sorry, I just wanted to let you know that Steve has joined. You told
Oh,
us
great.
to.
Steve, hi. All right, so this is what we do in field theory. Now, you can ask about whether this can diverge. An amplitude like this could possibly diverge. There are two places you could think about. As T2 goes to infinity, what happens? The only states that will survive are the lightest ones here. In particular, the massless ones, unless they're, God forbid, tachyons or something. Otherwise, the massless ones are the ones that survive. So any divergence that would happen here must be thought of as an IR divergence, an infrared divergence. So infrared divergences live up at the top end here. Whereas as T2 goes to 0, the suppression here, this Boltzmann-like suppression goes away. And so every state is now contributing. And so there's a complete pileup of all the states. And so how many states you start keeping having as you're going up to infinity, that's a UV feature. And so UV physics is what's happening down here at this limit where T2 goes to 0. So IR up here, UV down there. This is the behavior as T2 goes to 0. Infinity, and this is what the behavior as T2 goes to 0. And then if there are divergences, what do you do in field theory? Well, you put a cutoff in. And so you have some upper limit here with a cutoff and a lower limit there with a cutoff. And you introduce either one as needed. And this means you're introducing two new mass scales, an IR cutoff, a UV cutoff. But okay, there you go. This is field theory. Okay. All right. Now let's play a hypothetical game. Let's ask a question. Field theory. What if our theory happened to have an exact symmetry under T2 goes to 1 over T2? What if? Now, this is not a field-theoretic symmetry. In fact, I'm going to explain in a few slides why you could never actually have that in field theory. But let's pretend. If I did have it, what effects would it give rise to? How could we interpret this? Well, the first thing you see is that this would be some sort of symmetry that would flip across the T2 equals 1 line. The bottom and the top would become kind of the same because you have a symmetry that relates them. Well, the strip is invariant under that symmetry, so maybe you could have it. The measure is invariant under that symmetry, so okay. So what I'm saying is, what if the partition function also was invariant? In that case, you would have this symmetry. Well, in that case, you know what you would say. You would say the top part, let's call this the top half of the strip S1, and the bottom part S2. You would say the physics from S1 and the S2 regions, these two physics become identical. In other words, you'd say S1 and S2 obviously provide redundant descriptions of the same physics. Or in other words, the UV divergence down here must now become the same as the IR divergence up there, and therefore attributable to the same underlying physics, because you have this symmetry that you've assumed that relates T2 to 1 over T2. All right. Now, this should sound familiar. When you have a redundant description, it's like a gauge symmetry. And S1 and S2 are like two different gauge slices, two different descriptions of the same physics. Now, in this case, unlike real gauge symmetries, there are only two gauge slices, S1 and S2, and the overall factor of 2 that you get from integrating over the whole thing, this extra factor of 2, is like a gauge volume. But if that's the case, then you know what to do. You're supposed to divide out by the gauge volume and choose only one gauge slice. So if we had this symmetry, T2 goes to 1 over T2, that's what we would do. We would fold the strip across this line. We would turn it into this and say, this is just one gauge slice. This is all we should integrate over. Now, you could fold it the other way and just integrate over S2 instead and not just S1. But either way, you would pick one. And so if we did that, then we would integrate over S1, but not the total strip, just S1. We would have truncated the strip to just one slice. This would eliminate that spurious factor of 2 from having a double copy. And of course, we could have chosen, as I said, the other way and keep S2 rather than S1. But what this folding implies for UV versus IR physics is that the bottom part, which was UV, is folded onto the top part, which is IR. In other words, this is now both copies simultaneously. There's no longer a unique up or down direction here on this piece anymore. We've made it non-orientable in string language. We've lost the notion of an up or a down. We've lost the notion of UV up versus UV down versus IR up. All directionality is lost. In particular, the two divergences, the IR1 up here and the UV1 down there, have been folded on top of each other. There's now only one divergence. You can call it UV or you can call it IR according to your choice or convention, but it's a meaningless distinction. This is really critical. We've merged the two. Now, this nightmare only arises if you actually have this symmetry. So can this ever really happen in field theory? The answer is no, not likely. After all, the strip is invariant. We said that, it's true. The measure is also invariant, yes, but we've also had to assume, therefore, that the partition function was also invariant. And that's kind of hard to arrange, because if you look at this, this is a sum over all states with this Boltzmann-like suppression. And then if we're going to imagine this T2 to 1 over T2 symmetry, each T2 up here gets inverted in the exponential. And still we're summing over all the states, but now these are exponentials of 1 over T2. And the only way a sum over all the exponentials with 1 over T2 could look like a sum over all the exponentials with T2 is if there's some magic identity, a mathematical thing. Now there are. Here's one. It's called the Poisson resummation. Here's a sum over things with a T, and here's a sum without the T, with the T downstairs, and yet they're equal. So there are, and this is just one of a whole series of similar identities involving infinite sums of exponentials. But notice already the problems. You can do this, but you need infinite towers of states, which you're not going to have in field theory. And this is a rather sick thing, therefore, from a field theory perspective. You also need a very tight balancing of the masses and degeneracies at each level. Notice this doesn't allow you to have numbers that grow exponentially at each level or anything like that. And so you have to, this all gets very tight. And you really wouldn't expect to have any field theory way of having this emerge in any natural, sensible model based on point particle physics. Okay, but what I'm telling you now is that this is actually what happens in string theory. We don't always express it this way, but this is exactly what happens. You've already read, those of you that are familiar with closed strings know what I've been doing here. So now let's just talk string theory. So I'm going to be focused on closed for the whole talk. Let me just be very careful and tell you all, you string theorists, that we are focusing on closed perturbative strings. This is a huge class. It includes type 2 as well as heterotic. When I say type 2, I really mean type 2. Before the orientifold, I'm not talking about type 1, type 2. As well as heterotic, formulated in any number of spacetime dimensions with any spacetime compactification manifold or orbifold, with or without spacetime SUSY. No restrictions on particle content, gauge symmetry. I'm only assuming closed, because closed is what I need to talk about. Because if I am talking about closed strings, and here is my one slide of everything you need to know about string theory for this talk. Here it is. We're going to replace point particle zero-dimensional points with one-dimensional strings, closed. If we do that, then a one-dimensional world line becomes a two-dimensional world sheet. And therefore, a one-loop amplitude looks like a torus. We'll get to that. And then the only thing you need to know is that excitations of on the world sheet are the particles in space-time. And the excitations on a closed world sheet are like waves. They can propagate clockwise or counterclockwise. This is called left movers and right movers. And what in field theory is the mass becomes in string theory two separate contributions for closed strings, a left-moving mass and a right-moving mass. And their average is the mass that you have in field theory. And the number of ways of getting a particular mass is related to the number of ways of decomposing these numbers m left and m right in terms of contributions from underlying quantum excitations on the world sheet. So it's the numbers of ways of partitioning an integer into the sums of integers, and these numbers grow exponentially. So that's the Hagedorn phenomenon, if you want. That's why string theory has numbers of states that grow exponentially. Okay, that's all you need to know. So here we go. How do I calculate the same quantity, the one-loop vacuum energy, the Coleman-Weinberg effective potential, in string theory? Well, we had this diagram in field theory. That puffs out in string theory to become this, a torus, which has these two cycles. And the Schwinger proper time, which described the length of the circle, the length around the cycle, and then we integrate over all lengths. Well, now we have two lengths. We have a length this way, but we also have a length that way. And so this actually generalizes to the ratio, kind of the shape. How long is this length compared to that length? Is this a long, skinny torus or a very small, fat torus? We want to integrate over all the shapes without overcounting. And so that's what we care about, not the volume, but the shape. Okay, so how do we describe a torus? Well, let's just remember a torus can be described as two identifications, an identification around this cycle and an identification around that cycle. So I can imagine a plane of the two coordinates on the torus, y1 and y2, and we introduce two cycles. This is identified with this, and this is identified with that. In other words, the first cycle just says if I go around in this direction horizontally, and then I come back, there's a radius r1. If I go around in the other direction, there's a radius r2, but what is a bit perhaps surprising is that there's actually another possibility. I can have a little twist built into it, a theta. And if I do that, then what I'm saying is as I go around, y2 goes, if I go in this direction, I not only come back and identify it again, but I identify it having shifted a little bit. So that's what this extra theta is. So a torus can be described by three real numbers, r1, r2, and that theta. These are the two cycles of the torus. And we don't care about the volume. We only care about the shape. This is we're going to integrate over all possible shapes, because that's like integrating over all Schwinger proper times. And so to not care about the volume, I can rescale this. Let me just bring this number to 1. And then whatever this number becomes when I rescale, if I imagine this is a complex plane, y1 and y2 are the real and imaginary parts of some variable, this number is a complex number tau. And this is actually what it is. This is the number tau. And tau describes the shape of a torus. All right. And so what am I supposed to do? The torus shape can be described to a complex number tau in the upper half plane. The recurring cycles of the torus, as I go around and around the loops, I just generate a lattice in the plane. So the question is there any redundancy in this description? Are there different values of tau, in other words, that give rise to the same fundamental cell, the same lattice? Because that would be the same physics, and we don't want to overcount. Remember, gauge slices. So here's the lattice associated with some number tau. It's obvious there is at least one other value of tau. Here it is, tau plus 1. Same lattice. Well, if that's true, then tau plus 2 is also the same lattice, so you get that whole series. Okay, fine. Is there anything more complicated than this? You can beat your brains out. It actually turns out that there is one other thing you could do. You could do an inversion, -1 over tau. If tau is in the upper half plane, -1 over tau is another complex number also in the upper half plane. This doesn't look like the same lattice, except that, of course, it is only rotated. And literally, when I made this slide, I grabbed this little lattice I had drawn, and then I just rotated it. So trust me, it's true. It really is a rotated version. And of course, how I orient it in my little slide doesn't mean anything. So another set of equivalent taus is this. I can not only shift, but I could also invert. So these are what happens when I shift, or I shift and then shift. Here's what happens when I invert. But of course, now I can do all the combinations. I could invert and then shift, invert and then double shift, or I could shift and then invert, or shift, shift, and then invert, or shift, invert, and shift. And there's no end to this. And the set of all of these, if I bring all these fractions into the common form, they will all take this form. A tau plus b over c tau plus d, where a, b, c, d are integers, which have this determinant-like structure ad minus bc is 1. And so what I'm saying is that this is called the modular group. Of course, you knew that's where I was heading. This is modular symmetry. For any tau, all of these describe the same torus. If tau describes a torus, any number, AD minus BC is 1, any number here also describes that same torus. Okay. I'm going slowly because we're going to get deep into modular symmetries, and there's going to be a lot of surprising things. So we got to be very sure we understand everything. So the modular group describes the tau redundancies inherent in describing tori. This is classic string theory from 1970s or 80s. Tori are therefore unchanged. They're technically conformally equivalent under all transformations like this. And this is a group, it's infinite dimensional, we can call it gamma. And all I said is that you can generate this by shifts and inversions, T's and S's, and each mapping, I kind of figure I could write it in terms of like a word. First I shift, then I invert, or I shift twice and then invert, and so forth. Okay. An important subgroup is gamma prime. The subgroup of this generated just by shifts. That's a group by itself. Okay, so now the complex upper half plane of tau describes all possible tori, but the redundancy group, gamma, the modular group, describes the conformally equivalent ones. So it's just like a gauge theory redundancy. So what then is the subregion, the single gauge slice that captures just one copy of each torus without overcounting? Well, let's start with that whole upper half plane, but now let's say, what are the redundancies? Well, the first one is I can have that T generated shift. So obviously I don't want to have things that are shifted, so let me just choose to focus on a nice representative region from -1/2 to +1/2. That's the strip we had before. Hello, that's nice. But I have to do something more. I have to also mod out by the other generator. The other generator takes tau to -1/tau, or the modulus to 1/the modulus. It's not obvious that that alone is enough to restrict us to the modulus bigger than 1, let's say, relative to smaller than 1, but it turns out to be the case. And so this becomes a representative fundamental domain of the modular group, meaning that every point in here is conformally inequivalent, and anything outside is identical by modular transformations to something inside. So we can this is the gauge slice. And this last step is going to be the whole key to this talk of going from the strip to the fundamental domain is like relating field theory, because this is what we had in field theory that we integrated over in string theory. This extra step is how string theory and field theory are deeply related, and we're going to use this to build everything. And so this is the point. So how many gauge slices, how many copies of this fundamental domain F are there within the strip? Well, remember, in the previous case, when we just did a folding T2 to 1/T2, there were 2 copies, the upper and the lower. Well, now it's more complicated, because the answer is that this is the whole modular group. This is the modular group generated just by T alone, the subgroup. And so the answer is the dimensionality of the coset, and it turns out to be infinite. Infinite? Yeah, you can see it. Here they are. This is the fundamental domain up there, going all the way up to infinity, but I'm not going to keep plotting yellow all the way up. If I apply tau to 1/tau, -1/tau, the inversion I get of the fundamental domain, this is the inverted version of the fundamental domain. It doesn't fill out the strip. But there's another thing I could do. I could, for example, shift once to the left, then invert, and I get this region. Or I could shift 1 and then invert, and I get this region. Or I could shift twice and invert. Or I could shift once, invert, and shift again. I could keep doing these things. And each one fills out another piece down here. And the sum of these infinities is the strip. So there are an infinity of domains here. Each one is equally valid. I could choose to do string theory in this red domain. I never would. It would be very complicated algebraically, but I could. Together, these domains completely fill the strip, and each domain has a unique UVIR point. For the red, it's all, for the yellow part up here, it's all IR. Sorry, yes, IR, all the way up to infinity. Every other one, however, never touches infinity, but they all touch the UV. They all have a cusp down here at the UV. At the UV. Every one has a place where there's a UV, because each one has to have that same possibility of having a UV or IR cusp, where there could be a divergence. Up here, we don't normally think of this as a cusp. At T2, it goes to infinity, but you can. Because it's infinitely far away, this T1 direction is relatively small, so it's also a cusp. Okay, so that's the game. Now, these look like weird shapes, but they're really not. They're just pieces of lines and circles. And that makes sense, because linear fractional transformations, which is what we're talking about here, map lines and circles to lines and circles. So this is what you get. In fact, this whole modular thing, you may know the phrase modular furniture. Some mathematician who also knew how to do something with his hands and do things in the in a woodworking shop has actually made what's called the modular cabinet, and here it is, and this is the fundamental domain of the modular group. You can order this online if you want. I believe they can send it to you, but anyway, there it is. I was so shocked when I saw this online, but this is the idea. So in string theory, Relative to field theory, what are we supposed to do to go from from field theory to string theory? We are supposed to fold the strip into the fundamental domain. So we take this and we fold this part onto this part, this part onto this part, this part onto this part, this one, then this part onto this part. We work our way up, this onto this onto this, and we keep going. There's an infinite number of folds, but eventually we wind up here. This is the origami. Once all this folding is done, all the cusps lie on top of each other up at infinity. UV, IR are all there. So to go between field theory and string theory, well, we see already what's happening. The unknown scale we had before, it's the string scale. No surprise. The strip has become the fundamental domain. No surprise. The T1, which was a dummy variable in field theory, had no meaning, now becomes the real part of the torus, modular parameter tau. T2 is now the imaginary part. That's why this is T1 and T2, and this is the same. It's the tau that we had before, the shape of the torus. The partition function used to depend only on T2 because there was no T1 that had any meaning, and it depended on the mass. Now, in string theory, the mass part still only depends on T2. This is the field theory-like part. But the stringy stuff is that there's a dependence on T1 as well, tau1 as well, and that's not the sum, which is the mass, but rather the difference. This is the stringiness. So the T2 the behavior is like field theory. The T1 direction is the mass differences. This is the stringiness. States with m left equals m right don't have this part. And those states are field theory-like. Those are called level-matched physical states in string theory. They're the in states or the out states. Why? Because they're like field theory. They can be external states. Any other state has no field theory analog, but they contribute significantly within the amplitudes. These are the off-shell states. They're in the Fock space of the string theory, but they are not field theory-like. Okay, and I want to say that modular invariance has compelled everything I've told you about, and it's unavoidable. This is the symmetry group of the invariances of tori. The moment you have a closed string, you have this, all of this that I just told you. It's baked into string theory from the beginning. It's basically reparameterization invariance. Physics shouldn't depend on the worldsheet coordinates. But sometimes people call modular invariance a one-loop symmetry because it ensures the consistency of one-loop diagrams, the reparameterization for one-loop diagrams. But this terminology is misleading because when you talk to a field theorist, I'm warning you, they say a one-loop symmetry means that it's violated in two loops. It's an approximate one-loop symmetry. No, this is not true for modular invariance. Modular invariance is an exact symmetry of the partition function and of the entire spectrum of states. What it is, it's motivated by the consistency of one-loop diagrams, but it itself is an exact symmetry that applies always. You cannot break modular invariance by small amounts or by interactions, just like you can't break ward identities associated with gauge invariance by having gauge invariant interactions. This is powerful because what this means is that phenomena such as phase transitions may deform the theory as you go through the early universe and you're cooling and going through different kinds of transitions. And they may change which are the degrees of freedom. Are they hadrons? Are they quarks? But you can never break out of this. You're always going to go from one modular invariant theory to another. This means that modular invariance is, if you believe in closed strings, modular invariance is going to be your theory of UV-IR mixing. And what it says is maybe the way to think about hierarchy problems, which is where we're heading. So you might ask, do higher loop diagrams require other symmetries that are exact? The answer is actually no. It's been proven back 30 years ago, 40 years ago, Kawai, Llewellyn, and Tai, that within certain closed string theories, amplitude factorization and physically sensible state projections in string theory together ensure that one-loop modular invariance automatically implies multi-loop modular invariance. So this is enough. It stops here. Very nice. But the consequences for the physics, and here's where we're really going to start doing the things that we care about, the consequences of folding S into F are profound. The lower portions, because this is what we've done to the field theory to make it into string theory, the lower portions are folded upwards, as we saw before. We could have, of course, chosen to fold into SF or any of these others, but there's no longer a unique up or down direction, no notion of increasingly UV or IR directions. There's only one possible divergence. You can call it UV or IR. And so this is a meaningless distinction, just like the T to 1 over T2 example. In string theory, if you hear people talk about, for closed string anyway, a UV divergence or an IR divergence stop them. There's only one divergence, and amplitude is divergent or it is not. Those field theory words don't apply. So this is like the T2 to 1 over T2 example, but there are one additional feature. Infinitely many foldings are required. It's not just like the 2 foldings before. So we're dividing now by an infinite gauge volume, infinite. Or in other words, an infinite number of field theory divergences are eliminated, leaving only a single string divergence. So modular invariance not only relates UV and IR divergences to each other, but also softens them since we're dividing out by an infinite number of copies. Essentially, here's one of the biggest takeaway messages you could take from this talk. Essentially, some of the divergences of field theory are now reinterpreted as the spurious gauge volume associated with modular symmetries and thereby eliminated. This is why string theory is finite compared to field theory, or a lot of the finiteness properties. Basically, you could take this and invert it, unfold it, and put it back. So each string divergence is unfolded into what would appear to be a combination of UV and IR divergences when you separate it out and start building it up again in field theory. So what we're saying is that the IR divergence that you would have if you were in the F description is the same as the UV divergence you would say if you were in, let's say, the SF description, but it's just one divergence. You can call it UV or IR, but this one divergence, equal sign here, is equivalent to or related to, on the strip, a certain combination of IR divergences and UV divergences on the strip, a combination of them, but this produces an overabundance, an infinity of those, and so you need to divide out by the number of states in the coset. This is the relation between divergences in field theory and string theory. This is the number of redundant copies. Okay, so if we consider the cosmological constant, this is it in string theory. It's the partition function over the fundamental domain of modular group, blah, 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 as we said before, where this is the sum. Turns out, well, yeah, this is actually now finite, just by this argument, because when you mod out by everything, those infinite number of divergences go away. This is remarkable. This is true even without supersymmetry. Non-supersymmetric string models, and by the way, if you think there aren't, I remind you of the SO16 heterotic string. I remind you of all of those. There are plenty. There's a landscape, if you want, of non-supersymmetric tachyon-free heterotic strings. Tachyon-free means that they're stable at tree level. I'm not talking about higher loop stability, but certainly at tree level. So there are plenty of these things, and even for them, lambda is finite. Remarkable, because in field theory it's quartically divergent, but in field theory it's quartically divergent, but in string theory it's actually finite. You could ask, well then, how is modular invariance constraining the spectrum of states? Well, it must be doing something. We're back to that question again. The partition function had to have a modular symmetry, which means it's invariant under the 2 generators of the modular group. Well, the partition function itself here is a sum over all the states. So how are all the states arranged in such a way to ensure this miracle? You know, a simple question, it's very complex to answer. It's a complicated mathematical problem. It requires some knowledge of the products of sums of products of Poisson resummations. You need modular function theory and number theory. Anyway, of course, if you have supersymmetry, then for every boson there's a fermion, Z is 0. Okay, that trivially satisfies things. But even without SUSY, what happens? So this is actually something I studied 30 years ago. And the answer is that although you might have SUSY broken, there's always a hidden misaligned SUSY, which is basically another way of saying modular invariance in a tachyon-free theory. There's always a misaligned SUSY that has to remain in the spin spectrum. What is that? Here it is in a nutshell. I'm going to explain misaligned SUSY to you. Let's imagine we had a simple little theory of bosons and fermions. Let's imagine the bosons lived at energy levels n equals even, and the fermions lived at energy levels n equals odd. Let's plot as a function of the levels n in string theory, massless and going up. This is the number of bosons minus the number of fermions. So bosons are positive numbers, fermions are negative numbers. Misaligned SUSY says the functional forms always have to cancel. That's all it says. That this number here, this dashed line, has to match the dashed line. Now that's actually kind of profound. This is not the way field theory works. Let me explain. SUSY, of course, is the special case where the sectors are aligned. Let's imagine we shifted these n equals odds all the way back down to evens. So we align it. bosons are at n equal even, fermions are at n equal even. Then this number, whatever it is, would have to match that number in the white dot. If this is 3 states bosons, this is 3 state fermions. This is now 7 states, this is 7 states. This is 19 states, that's 19 states. That's Susie. They're aligned. What you can do in string theory, I'm telling you, you can never do more than misalign a sector. You shift them upwards. Now that looks like splitting. That's like what you do when you break Susie in field theory. You just introduce a splitting. But no, because what's happening here is that you have to stay on the functional form. And these are always monotonically growing, and well, in this case, in the negative direction. So this 3 here is now a 4. This 5 is now a 9. This 15 is now a 19. So when you shift, something has to happen in the twisted sectors to bring new states down from infinity to populate here as you keep going. That's what modular invariance is guaranteeing, that as you misalign your sectors, new states have to be reshuffled throughout the spectrum, UVIR mixing, in order to guarantee that you stay with still a functional form that cancels. So what do you wind up with? Something like 5 minus 9, 13 minus 21, 73 minus 119, 282 minus 793, etc. This is what happens in string theory. There's no boson fermion pairing anymore. This is not Susie, this is not field theory Susie breaking. This is something else. But this is what happens. And this is a general feature in any closed string model. Type 2, heterotic, anything. This is the way in which the spectrum of string theory manages to configure itself at all mass levels to maintain finiteness, even without Susie. This is just a sketch. Here are real string models. These are just random heterotic string models that I built a long time ago using the free fermionic construction. If you remember back in the 80s, those things. Here they are, always. There are many envelope functions, but always there's an exact cancellation. Always. So I've shown you now the strip region is infinitely larger than the F region, and we know how to relate them by this folding, this origami. But is there another way to relate? Is there a corresponding way to relate the integrals over those regions? Is there a way to extract the infinity in field theory and thereby get the string result over the F? This would really be a way of expressing string theory amplitudes in field theory language. Well, it turns out there is. There is a way to do this. This was first developed by 2 mathematicians, Rankin and Selberg, in 1939 and 1940. And what they said is that, well, let's concentrate on cases where the F integral, the string integral, is finite. Well, the strip integral still is going to diverge. It's got those infinite number of copies of this, so there's going to be a divergence. But it turns out, here's the field theory, the string theory, finite integral. Here's the strip. It goes from tau 2 to 1, 0 to infinity, and tau 1 from minus tau. But you deform it slightly by deforming, you introduce a new parameter S, which is how much you deform it. This still diverges, but then you take the residue and you get, the claim is, the proof, the theorem is that you get back this. So what we're saying is that, yes, in string theory, it's finite. In field theory, it wasn't. But the field theory one wasn't. It had a pole, but you deform it slightly and then take the residue, which is a finite number, and the string amplitude is the residue of the divergent field theory amplitude. My gosh, that's the relation. Now, this was proven by mathematicians. There's another way, and what that means is that only field theory-like states, you can express everything in string theory as sums of field theory states. That's what this tells us. We'll get to that in a minute. So you could also express this residue by taking an inverse Mellin transform, if you know what that is, and you can express it this way. And this was done by another mathematician, Zagier, in 1981, and 10 years later, Kudasov and Seiberg reintroduced this into string theory, but actually it goes way back. And so, as usual, the mathematicians were there first, but they didn't know what it meant. So anyway, here it is, and this is really a remarkable result, because we now know that the full string amplitude, which depends on all the string states, physical and unphysical, is related to hi.
Hi, I have a question. So is
Yeah,
there a formula for this formula in like other like ring surfaces, or is it like specific to torus?
This is shown for a torus.
Okay.
And I don't know if there is a multi-loop version of this. I could see lots of reasons why there might not be, but on the other hand, there are multi-loop modular invariances as well. I don't know. Maybe Steve, Luca, if you know, jump in and say something, but I don't know. It would be complicated. It's very nice to know this, though. Certainly, this is important.
Yes,
I'm
yes.
just going to jump in and say I don't know, but
the fundamental domain still lies in the upper half plane. So
Well, the fundamental domain at multi-loop is complicated because a two torus has more than just a single complex number to describe its shape moduli. Steve, were you going to say something?
yeah, I mean, but here's the thing though, like still you can uniformize in some fundamental domain in upper half plane, right? Because you can write as like a h divided by some gamma.
Yeah,
and
you
gamma.
can do, okay, you can call this process unfolding, and you can always unfold. So there's got to be a relation like this. I thought you were asking, has somebody written it down? I don't know if the mathematicians have written that down, but yes, there is in principle a relation like this. Absolutely, yes.
Okay, good.
Just because of the group theory structure, yes.
Mhm.
Okay.
Is that what Mirzakhani did? When she
What?
tried-
Yeah, that's correct. Yeah, that's what I'm asking. But this relation doesn't seem like a Mirzakhani type of relation, really, right? Because that one is involving like sinh and hyperbolic length, but this only involves like the moduli. So that's why I was asking, like somehow can you just use the complex moduli of those surfaces to write a relation like that? Not the like ones that involve hyperbolic.
I would say there has to be a relation like this,
Yes.
but I do not know what it is, and I do not know if mathematicians have done it. Maybe they have.
Mhm. Okay.
The group theory structure almost compels that there be one like this, because you can certainly unfold that too. Okay, but anyway, everything we're going to do is coming from this relation, and you can see how much mileage we're going to get out of this. So this relation allows us to express string theory amplitudes in terms of supertraces over only physical string states. And this will ultimately allow us to understand how to extract a field theory language, an EFT, from string theory. Okay, so if we do this game of unfolding to the cosmological constant, the simple one-loop integral, we find two results immediately. The supertrace of one, meaning just count bosons and count fermions, in a prescribed way equals 0. Now, what do I mean by supertrace? Sum over the states, the quantum number A for whatever the supertrace that we're evaluating is, with the grading -1 to the f. But of course, in string theory, we actually have infinite towers whose numbers grow exponentially e to the m. So we have to have a little suppression factor here. This is e to the -ym squared, and then we take the limit as y goes to 0. Turns out this is a modular invariant regulator, so it's perfectly fine. And so what we're saying then is that if you do this over that string spectrum for any string, the number of bosons and the number of fermions, or in other words, the supertrace of one, just of nothing, is vanishing. True in SUSY, but true even without SUSY. Moreover, the cosmological constant can now be expressed as a sum over the states of the mass squareds. Just add the mass squared. So here we are again. Here's our picture of what we had. So just count this number, that number, that number, that number. That equals 1 according to this equals 0. And moreover, the cosmological constant associated with this, just take the mass squared of that times that, the mass squared of this, the mass squared of this, add those numbers up, and you get the cosmological constant. This is amazing. This is very different from field theory, where supertrace 1 would normally govern the quartic divergence of lambda, and supertrace of m squared would normally govern the quadratic divergence of lambda. Here, we're canceling the quartic completely, and even more, what we used to govern the quadratic divergence now governs the amplitude itself, the whole thing, not its divergence, but its value. So that's really remarkable. Okay. These are examples of the hidden cancellations that misaligned supersymmetry that's running through the whole string spectrum is doing, suppressing divergences and assuring the finiteness of string amplitudes. You knew string theory was finite, but maybe you didn't know level by level how this happened. Now you see how it's happening. In fact, these relations I just showed you for supertrace 1 are only the tip of the iceberg. We have shown in our paper, it's due to come out soon, but we already put it in an earlier paper because we just wanted to quote the results. For any modular invariant operator insertion X, anything, combinations of charges, helicities, doesn't matter. Supertrace of X is always vanishing. And the amplitude itself, just like the amplitude here was the supertrace of M squared, that generalizes as always the amplitude of supertrace X times M squared. In fact, this is in some sense a definition of what modular invariance means. These are the operators for which these results hold. This is, I think, incredible. Anyway, all right, Higgs mass. Good thing we have another half hour. So let's use this technology to calculate the Higgs mass. Now, again, we're focusing on these strings. Let me remind you, though, that our goal is not to evaluate a numerical number for the Higgs mass within a particular string model. Other people like to do things like that. I don't think that's interesting. I want to evaluate a modular invariant framework to create a framework for these calculations. That way we'll get general phenomena that hold across all string lines. So what do we mean by Higgs? A scalar field, here's my definition, sitting at the minimum of a potential whose VEV affects the masses of the particles in the string spectrum regardless of the gauge symmetries the VEV breaks. Therefore, we're talking generally about the standard model Higgs or other kinds of Higgses, Higgses, other moduli, any scalar field. Okay. And I just want to say that what we're doing now to do such a calculation is an issue in string phenomenology, which is extracting low energy phenomenological predictions from string theory. But I have to make an editorial right here. We are not going to practice string phenomenology in the usual way because we care about hierarchy problems eventually. So we want to be sensitive to UVIR implications. The traditional approach to people who practice string phenomenology for 30 years has been you start with some vacuum, you pick a string model, you enumerate the massless states only. You then construct a field-theoretic Lagrangian that describes the dynamics of those states like, oh, here's something that looks like a non-abelian gauge boson. I create the symmetry, F mu nu, you write all that down. And then you analyze that Lagrangian using all the regular tools of quantum field theory without further regard for the origins of those states within the string model. There was an infinite tower of states, we threw it out. We broke everything I just showed you. Now, that treatment may be well for certain purposes, but obviously, by disregarding those infinite towers of states that necessarily accompany these low-lying modes in the full string theory, we're implicitly disregarding all the underlying string symmetries that endow string theory with all those remarkable UVIR properties, that finiteness. You know, that's what field theory is sick. That's why we have divergences. String theory, I think, should get rid of this. We believe this. So we are pushing, Steve, Luca, and I, that people should be thinking about doing string phenomenology, respecting modular invariance, keeping all the states and keeping every operation modular invariant if you're dealing with closed strings. Now, you could say, well, that's silly. These states are at the Planck scale. Certainly, you can integrate them out. How could they ever play an important role for low energy phenomenology? Can't I just integrate them out and they would leave behind higher dimensional operators suppressed by powers of the mass scales of the states you're integrating out? Wouldn't that justify the usual treatment? EFT way of thinking? Answer, well, maybe not. Think about this. We're not integrating out one or two states. We're integrating out infinite towers of states. Who said you can do that? Even more severely, the numbers of states in those towers are growing exponentially growing degeneracies. No one says you can integrate that out. And how could that leave behind a power loss suppression for higher dimensional operators when the degeneracies of these states are growing exponentially? The usual EFT expectations about disregarding these infinite towers of states may not apply, is our point. It's in particular natural to expect that the infinite towers of states would particularly affect quantities such as the Higgs mass and the cosmological constant, which have positive mass dimension and are therefore sensitive to all the mass scales in the theory. You want to talk about Higgs masses, cosmological constants, divergences, hierarchies? You have to be dealing with all of this. So, okay, so we're going to retain everything. And modular invariance, as I said, is the ultimate UVIR mixer and enforces this balancing between low and high scale physics. So if we take string theory literally as a theory of physics, we should perform our calculations in the full framework of string theory, incorporating all of the towers of states. So let's do that. So Higgs mass, this is what we're doing. We're not trying to get a number in a model. We're trying to get a framework. And then we can see how an EFT might emerge. Okay, now our interest is in calculating the Higgs mass, not the Higgsing phenomenon. We want to know the mass of the guy when he's down here. So we want to work right here, exclusively within the Higgs phase, where the scalar field's already at the new minimum, and we want to study then fluctuations around this minimum, and we want to do all this without breaking modular invariance. Okay, well, the fluctuations of the Higgs are going to cause perturbations of the masses of the states across the string spectrum. That's what it means to be a Higgs. So let's let phi be the fluctuation of the Higgs field around its VEV in the Higgs phase. Well, then all the states in the theory could potentially shift in a phi-dependent way to some new values that are phi-dependent. They're functions of phi now. These mass shifts describe the response of the system to Higgs fluctuations around the minimum across the infinite towers of states. I don't know what these numbers are. In fact, some masses won't feel them, some will feel them. And that's how you're putting into the theory which Higgs are we talking about, which states are going to respond. So this is a formalism for all possibilities. So we're going to make all of the masses functions of phi, knowing that in many cases there'll be zeros here, and that means that we're not talking about those gauge symmetries. Okay. One thing you can learn right away is that the shift on the left movers and the shift on the right movers has to be equal by modular invariance. Otherwise, that would break the symmetry tau goes to tau plus 1. Okay, so we do this. Well, we now want to establish basically what is the shape of this, or at least the nearby the bottom, the shape of this Coleman-Weinberg potential, if you will. It's the same like the cosmological constant, only now in the partition function, we still have the masses, but the masses are now functions of phi. So the partition function through the masses is also a function of phi, and then we just take the curvature at the bottom. That's what the mass is, and here's the definition. So the recipe is very clear. Take the partition function, but the masses that we used to have in the exponential of the Boltzmann term, if you will, now they're phi dependent. So here it is, the masses are now phi dependent. We take two derivatives of the partition function, and what happens? We pull down from the first derivative a derivative with respect to the mass, and then we hit with the second derivative. That could either operate on the term we pulled down there by squaring it, giving a perfect square, or it could pull down another factor and then we get the square, or we could just operate with a second phi derivative on the term we already pulled down. So basically there are two terms that are now going to sit here when we take two derivatives, and this is an insertion into the summand. This is an x, and here it is. And so what does this mean? First, it depends only on the total mass, only on tau 2. It's field theory-like. This is the contribution to the total Higgs mass from each state in the theory. That's what it is. Notice it has a part that depends on tau 2 and a part that depends on tau 2 squared. That's going to be important for technical reasons, so we're going to write it separately as tau 2 and tau 2 squared, and this is an x1, and this is the x2, and the insertions are just this. So what am I saying? I'm saying that the full string amplitude, let me define the bracket notation to be the full string amplitude. Here it is, modular, fundamental domain, partition function with an insertion for any operator A. And then all we're saying is that with this clever, nice notation, that the Higgs mass is going to be given by the bracket with this insertion, tau 2 x1 plus tau 2 squared x2. All right, are we done? Now we just sum up all this and integrate? No, because it turns out that these x insertions into the partition function sum breaks modular invariance. This is not a modular invariant insertion. There's a subtle modular anomaly that needs to be taken into account. And to modular complete this, to make it modular invariant, it turns out you need to add a constant number. And this is a modular completion. And I can get into the details if you want. If the slides are going to be posted somewhere, you can see it. I've explained it all here. But basically, you need to add an extra term. Modular invariance forces it. This C is an order 1 coefficient that tells us how the particular Higgs field is realized in that model. So this is partly related to how did you embed the Higgs in the lattice of the gauge charges of the model, or if you will, am I talking about an SU5 Higgs or an SO10 Higgs, or am I talking about the standard model electroweak Higgs? All of that is buried in this number C. It's just an order one number. Okay, but I have to add this point. That's the thing. What does it mean physically? Well, actually, you can interpret it very nicely. The X terms, these parts, capture the effects of the mass shifts induced by the fluctuations of the Higgs fields. But in string theory, there's also going to be a gravitational back reaction. These are the deformations of the moduli arising from those fluctuations. They will also make contributions to the Higgs mass, these gravitational back reactions. They should be universal because they're gravitational back reactions, so they should be independent of the specific X insertions, and that's what these numbers are. So if we hadn't known about it and had calculated also the gravitational back reactions, we would get this number, because naturally we get a modular invariant result. But modular invariance is enough to bootstrap our way just from this to know that. And indeed, that's how we did it. But we recognize what this is. It's just a pure number. So this is the bracket of 1. And that's the cosmological constant. So now we already found something amazing. The Higgs mass at one loop is equal to the cosmological constant plus this other stuff. We have a relationship between the Higgs mass and the cosmological constant. Now, I just want to editorialize again. This is remarkable. We should never see, this is so not like field theory. In field theory, the Higgs mass is quadratically divergent. The cosmological constant is quartically divergent. The field theory never knows about a cosmological constant anyway, a gravitational thing. Field theory doesn't even know. A relation like this could never exist in field theory. But in string theory, we do know about the cosmological constant. It's part of the gravity sector. It's part of the Higgs mass. This is the gauge part. That's the gravity part. They're related in string theory. This is now finite. This can be finite as well. And so we have the possibility of a relation, and there it is. So all of that is amazingly stringy. And it's really intriguing, I think, that these relations join together precisely the two quantities, Higgs mass, cosmological constant, whose values lie at the heart of the two most pressing hierarchy problems in modern physics: scalar masses and cosmological constant. There's a deep relation here. We cannot exploit this, I'm sorry to say, to give a solution to either hierarchy problem, however. There's no way to constrain this number. We've tried. So this does not enable us to take that step, but it does provide a relation. This is probably part one of some solution that might come along. All right, so this is what we've learned so far. I don't want to bore you with the algebra, but what you can show is that the Higgs mass is also at most logarithmically divergent. It happens when there are x2 charged massless string states. And it's finite otherwise. So just like the one loop vacuum energy, the cosmological constant in any tachyon free closed string theory is finite, already surprising, we now learn the corresponding Higgs mass is at most logarithmically divergent. It's not quadratically divergent as it would have been in field theory. So modular invariance has induced a significant softening of the Higgs divergence, reducing what would have been quadratic UV into a logarithmic Higgs divergence. Notice I don't say UV, but it's still divergent, potentially. So we need to regulate it in some way that will enable us to extract results. Now, there are lots of regulators you could imagine doing, and in similar calculations for the gauge coupling running, Kaplinovsky had to deal with this question. And this is in his classic 1987 paper. And he removed contributions from massless states. There were reasons why that was the right thing to do for him. And those are the ones that give divergences. So, okay, it's a kind of blunt way to do it. Another way to do it is just to do a cutoff on how high you go towards your upper limit here. We're not going to call it UV or IR anymore, but we're just going to say there's a divergence up there and we're going to cut it. What does the cutting do? I just want to make a small point here. What the cutting does is tell you that your amplitude will depend on the choice of the cut T, and the cut T is going to depend like this. And if you look at this, it looks a lot like a normalization group flow. Here it is. It looks like an RGE. And if you did that, you would say this 1 over T looks like a mu, and here's a log running of a quantity. That's not a surprise, because if I cut my tau2 somewhere, remember that this is like a Boltzmann factor. So if I put a cut and I say everything above is not dynamical, it's too heavy, everything below a certain mass scale is not, then what you're doing is saying for any 1 over t, certain states are heavy and they're being suppressed, and certain states are light and they're contributing to amplitudes. And this is how we're extracting a running quantity in string theory. We don't normally talk about running in string theory, but this is how you can make connections back to field theory. And it happens by this t cut that you can now take as a floating scale mu. This is how you can do it. So this is a general identification for extracting an EFT if you wish, but here's the problem. That's not modular invariant because you can't just impose a cut somewhere in the fundamental domain. Instead, you need to deform your theory somehow in a modular invariant way to make it finite. So you insert instead a modular invariant function here, which suppresses things near the places where the divergent cusps could be and otherwise don't. G, this function has to have certain very specific properties, and you can work out what they must be for consistency. We have only been able to construct one function that does it, but one is enough. We cannibalize a previous work by Karitzis and Kunas, who also calculated these things and tried to get some parts of modular. They did it in a modular invariant way, but they didn't do it in a way that leads to a field theory result. So we've improved on it a little bit, but basically the idea is that our function is going to depend on some circle some circle partition functions. If you recognize all this, don't worry about it. This is not the point. The point is that there is a function that suppresses things. And here's what
I have another question.
Yeah,
So,
let me just finish this.
Sure.
So basically tau2, and here's the plot of the function, and you see what happens. It suppresses things as you exponentially strongly, in fact, which is what you want. It's a good regulator as you go up towards tau2 goes to infinity. But notice it's doing it smoothly in a modular invariant way. That's what we need. Yeah, go ahead.
So, okay, so there's going to be like some cutoff coming from this procedure. Say this is
here's effectively the cutoff.
Yeah, but the effective field theory has a different cutoff, right? It's a Planck scale. So this procedure.
I didn't say anything about where it is. This is Planck scale, if you wish.
No, like my point here is that there's two different cutoffs. That is one in the AFT and one coming from your regularization procedure. So how would you relate those two cutoffs?
Those are the same. Those are the same. In field theory, what you do is you impose a regulator, and that gives a floating scale, and that is your scale. If I could translate what you're saying into what I think you're saying, the language would be: there's one on the world sheet, and there's one in space time, right?
Yes.
That's it. And the world sheet variables and the space time, and they're identified this way in order to make an EFT. Or in other words, when I said this before, the idea is that you're identifying an EFT in space time from the world sheet. This is going to be a really important point, so I'm glad you emphasized this. I'm trying to go a little fast, but you're absolutely right. So we are going to be suppressing this. So what I'm saying is G has this property. Any G we need is going to have this property. Everything I'm going to show you really doesn't depend too strongly on the particular value of G, this G function. The point is there has to be a modular invariant suppressor on the fundamental domain that suppresses as you go toward tau, going up to I infinity.
But like if you just consider string field theory and how we are supposed to do it in string field theory,
I don't know string field theory.
Yeah, so the problem is that the way we use it's not modular invariant, right? Like say that I want to do like a one punctured torus, then there's going to be a flat cylinder which breaks the modular invariant. So like I don't understand how they will relate.
I cannot talk to you about this. I don't know string field theory.
That's fine.
Let's
just asking like
questions. I'm sure there's a way to do everything I'm talking about, but I don't want to swear it away because I don't know.
Okay, sure. Thank
but
you.
You
so
follow
much.
what I'm doing, right? Okay. All right. So in the end, here's what we had. The Higgs mass should be related like this. And this thing has two kinds of contributions from the X charge states and from the back reactions. Now, this would normally be diverged, but we're going to deform our amplitude by having the G function here. Now it's finite, so we can use all the Rankin-Selberg, take the residues, and express this amplitudes in terms of supertraces only over physical states. Now, even this calculation is a mess, but we have people like Steve and Luca who are able to push through infinite mess. And here is the result. So it has two parts. This is the part that depends on the X assertions, and this is the gravitational back reaction, the cosmological constant, the first term, multiplied by something. And the answer is this. Now, this, don't spend time looking at, this is Bessel functions galore. Each K here is itself a sum, an infinite sum of rescaled Bessel functions. As I said, I could never do this. This was Steve and Luca. But anyway, this is what we get. It's kind of like fractals, if you think about it. Maybe there's a deep connection. I don't know. But if you stare at it long enough, certain things become apparent. Whoops. One thing is, this is supertraces over the charges times other contributions. And this is supertraces over the masses. And this is mass to the zero, if you will, number of bosons minus number of fermions. That's all it is. Supertraces over charges and over masses. That makes sense. Here's what happens if you take the limit as mu goes to 0. Only certain terms survive, and what you get in the limit is it depends on the cosmological constant and this supertrace of x1 over all states. Cosmological constant, remember, was a supertrace over m squared over all states. This is supertrace of x1 over all states. You would not expect in string theory, in field theory, that you would ever have all states contributing to an IR limit. But this is the UV-IR mixing. The IR limit is the UV limit. Of course, it's all states. That's the only way it could have been. Because this is UV-IR mixed and invariant. You could look at this thing, which is the contribution to each state, each massive state per unit x2 charge. It looks like this. State is frozen out at low mu, much less than m, for whatever the m is. Up here, it's an EFT-like running, logarithmic. In between, there's interpolation. The particular shape of it is kind of stringy. At least it's governed by these Bessel functions. So we call this a dip. Everything else is subleading. And when you put the pieces together, you get this. This is the running of the Higgs mass in string theory. In the deep IR, you get this asymptotic value that we talked about. You go through a dip. You then come to a logarithmic parallel running. And then you enter a turn. So this is the EFT type region. Then you enter a turnaround region where you have as much UV as you could never get more UV than this. That's why I'm going from red background to blue. Because after this, you enter a dual region where it all goes backwards. And you get a dual deep IR, which is the deep UV. There's a scale duality, mu to 1 over mu. And this is not a surprise. What we see it implies, though, is that there's a maximum degree to which you can ever probe UV, if you want to call that UV. Increasing mu only reintroduces the IR-like behavior all over again. The background colors indicate this. The theory must have a vanishing beta function at the self-dual scale. Even the deep IR, therefore, has to know about the dual deep IR in which all states contribute. That's why it's all locked together. We know things like this in string theory already. The depth of the tachyons determines the Hagedorn temperature, bottom, top. But here it is explicitly in terms of running. Why does we have this? Well, remember my statement. 1 over t is related on the worldsheet to mu squared over this. But we know modular invariance relates on the worldsheet tau2 to 1 over tau2. So any t, 1 over t could have been chosen instead, which is exactly this symmetry. Modular invariance compelled it. It was trivial. I don't think it's ever been noticed before in the literature, but here it is. Scale duality, we call it. Okay, so what then? How can you extract EFTs? You have to make a direction choice, which is UV to integrate out, which is IR to retain. This breaks modular invariance. This is a spontaneous breaking. Your choice is a spontaneous breaking. But we see now that because of scale duality, this is part of a deeper structure which exposes the role of EFTs in modular invariant UV-IR mixed theories. Here's the structure. This rho A squared, call that T. That's the worldsheet parameter. which is different from the space-time premise. I'm glad we had that question a few minutes ago because it's different. If I make the identification that mu squared over ms squared is t, then I have a line like this, which relates this variable to this, but I could have done the 1 over t map, UVIR mixed modular. I had to have also this possibility. And then we know that the IR limit here is the IR limit there, the dual IR, and likewise the IR is the dual IR. So what we learn is that there's a 4-fold structure, not a 2-fold structure. Your maximum possible UV is in the middle. That's where your symmetry is. And here you have a regulator symmetry. T has to go to 1 over T for self-consistency for a modular invariant regulator. And we have scale inversion symmetry, which maps this to that. And we wind up with a 4-fold structure. The EFT regions are out on the branches. You have to choose which branch you want to go on. There you've spontaneously broken modular invariance. But where is the symmetry fully restored? At the center here. So there's a 4-fold structure. And the EFT regions are out along the spokes. So the passage to an EFT requires choosing a spoke and thereby breaking the 4-fold symmetry associated with modular invariance. In other words, that picture when we went from UV up to IR sort of and then back down again is like going from here up to here and then back down again, or maybe back down again, or maybe back down again. I can't tell you which because they're all redundant, because of the 4-fold structure, but that's what we're doing, up and then down. This is what happens when you have a UVIR mixed theory. Okay, so what do we learn about EFTs? And I'm almost done. You have to spontaneously break modular invariance by choosing a branch. And then in certain ranges of scales, it's like an EFT, except the divergences are softened. It's not the same EFT you would have expected in field theory. Running is different. It's logarithmic, for example. And even in this region, the theory is sensitive to the infinite towers of states, not just the light states. Running is governed by supertraces over all the states. And the EFT behavior also cuts off not only when you approach string scale, but also when you approach the deep IR, because that's where you're sensitive to the deep UV. And so again, you're losing your EFT. Your caution, you have to be careful when you're thinking about EFTs. All right, I'm going to skip this. Well, I'll just say it. This, it turns out, is actually the phi derivative of that if you put the masses back in to be functions of phi, which means you can write what you had before, the contribution from the gravitational part. This was the contribution from the gravitational. This was what happens with the x insertions, but I said this is the double derivative, so you can write it this way, and you can make a covariant derivative. And so what you wind up with is a stringy effective potential for the Higgs mass. Basically, you now have a function where you get the cosmological constant is just the function evaluated at the bottom, and the Higgs is related to the curvature at the bottom. These are exact relations. Everything is finite. Coleman Weinberg were hoping you might get something like this, but they have divergences. It's complicated. It doesn't really work. Here it is, clean and simple. You can also use previous results to get a supertrace relation for what the Higgs mass is. Really nice. All right. Gauge couplings. I can do this in 2 slides. Although it was another tour de force, I'm sorry to say, but the paper is online. So this is with Luca and Steve. And here's the gauge coupling. And again, this is to 1 loop order. You can write it as a tree plus a 1 loop. So here's the 1 loop. You work out what it should be. It's the amplitude. Here are the insertions. There's a quadratic Casimir insertion. It needs to be modular completed. Surprise, surprise. Here's the space-time helicity charge. It's the helicity is -1/12, but you know what? You can't add a 1/12 to a charge operator because this is modular weight 2. This is modular weight 0. Can't do it. This also needs a modular completion. I don't know if anyone has ever discussed this before, but we had to figure it out. The modular completion is with the Eisenstein function. In other words, the Eisenstein function is the modular completion of the number 1. Which we have to add to an operator like Q, because in field theory it would be Q, the helicity squared operator -1/12, and you can't do that. That -1/12 can't be done. So there's an Eisenstein function. This introduces a whole host of complications and a very nice entwined structure. Never mind, you get this insertion, you do the same calculation, the rest proceeds as before, and now you get a picture that looks like this. a little bit inverted. The minus sign here became flipped the whole diagram. So there's a tree level, and then there's a one loop. I want to point out, again, a dip and everything, but here, look at this. If you have a large extra compactified dimension, as you cross the KK thresholds, you think you should maybe go from logarithmic to power law running, but you don't. And the mystery here is because there's going to be winding states. Remember, we're talking about closed strings. Now, winding states should be above the string scale, but remember, this is UVIR mixed. KK states and winding states are present here at all places and here at all places. And once you have your KK states, which would have converted you to running power law, the winding states cancel that. They cancel the running completely. This was a big surprise to us. It's discussed, not even discussed here. We hint at it here. It's coming. So I'm done. Future work. First is this non-renormalization theorem that we're working on now. Basically, you do lose your running. And there's a deep reason why, and we have made a theorem and we've proven it, and it's really very powerful. It's like SUSY non-renormalizations, but without SUSY, just because of misaligned SUSY and UVIR mixing, modular invariance. We found also in the course of our work, it was known already, but we really worked it out. Misaligned SUSY exists not only for off-shell string states, but also on-shell string states. Or rather, we knew it was on-shell. We now show it's off-shell. We'd like to study more complicated theories with interactions and vertices. How do these behave as functions of scale? Scale duality has to be a general property. What are the implications of scale duality? This means that the coefficients of all operators should run to zero slope at the self-dual point. Is this a fixed point in some ways? Does this lead to a new solution for the heterotic gut scale discrepancy? If you're old enough, you might remember that the Kaplanowski gut scale was not matching the value known from extrapolating bottom-up guts, 10 to the 16 GeV. There were many solutions conjectured, but we think this leads to a new solution, basically, and we're very excited about that. How much of this extends to open strings? Well, open strings don't quite have modular invariance, but the torus and the Klein bottle do, and then the open string sectors have orientifolded versions of them. A lot of this does survive, and there have been papers recently on this. And then finally, you can ask, okay, what about the gauge hierarchy problem? We still really can't say anything. It's my final slide. But what we can say is that the hierarchy problems, both for the Higgs mass and the cosmological constant, now have the same form. And these look like Veltman conditions. Years ago, Veltman wrote down supertrace relations, but he had supertrace relations over things that were lighter than the Higgs. He didn't know what the Higgs was, but it was over light states. This is over the entire string spectrum, but again, it comes out now from modular invariance. Another idea is that you can maybe exploit this dip region to make it possible that you run down from the string scale a long way, and then finally you hit this dip. And if that corresponds to the region where the Higgs mass squared goes negative, you would trigger electroweak symmetry breaking. You can work out what relations must apply to these x's to make that happen. And it's this. We have no reason to suspect that that is true in most models, but anyway, this might be another way to think about it. The final takeaway message: hierarchy problems assume traditional field theory relations between UV and IR. But string theory tells us that we have UV-IR mixing, softened divergences, even finiteness, scale duality. So I think hierarchy problems may not be as fundamental or survive in the manner we normally assume. So that's the big message. Thank you very much.
Okay, thanks, Keith, for this very nice talk.
My pleasure.
So I think we have time for at least one or two questions.
Sure.
So if anyone has any question, please unmute yourself and go ahead.
There's also email.
Yes, of course.
There's also the papers themselves, which are kind of long, but hopefully nicely written and easy to get through.
I have one more question, but if anybody
Yeah,
else
you're
has-
scary because you're asking things I don't know about, but go ahead.
No. So, okay, so you put this regulator, right? Say that I do it for some SUSY compactification. Then that amplitude, like say the say that take the couplings, the scale formula, and like the gauge coupling that you compute should be holomorphic function of the moduli, and there's a scalar potential contribution, right? So is your regulator respect that? Because it's better respect that. So how do you know that it guarantees that the holomorphic dependence?
The
Like
regulator,
for example, in string, yeah.
yeah, we didn't make it up. And I want to make it clear that you're asking a really good, important question. And one stab at an answer I'm going to give you, Steve and Luca are free to chime in. But the point is that this regulator, remember I said we cannibalized some previous work of Karitzis and Kunas. There is a physical interpretation to this. It corresponds to turning on fields in a background string geometry such that the conformal field theory associated with a flat 4D spacetime is replaced by the CFT associated with an SU2 level K Weston-Witten model. So there is a physical interpretation which renders the physics of it consistent. In other words, if I'm deforming the background, that's the regulator they were going for, a geometric regulator on the spacetime. And so I think, and we're just saying, okay, well, there's a function. We can just view it as a function and put it in, but it corresponds to a physical deformation of the geometry of the space. And so I think it should be okay.
Okay. So
Steve, you want to add to that?
So did I understand the question? You were asking about the holomorphy of basically mu, the energy scale. Is that right?
So what I'm asking is that like if I take a gauge coupling in supergravity, I have this running formula that has like a one loop contribution,
right,
the Planck mass over the mu, and that there's a scalar potential if there's a SUSY. So what I'm asking is that that formula has to have a very particular regularization procedure that is coming from worldsheet that should respect that effective field theories formula. So what I'm asking, like the regularization that you put, does it respect that, or like did you check it?
Yeah, no, it should do because so like Keith said, basically the original regulator of Karitzis and Kunas was based on a geometric compactification that respected all of those things. Yeah.
If it hadn't, I wouldn't be so confident. But the point is, there was a physical deformation of the geometry which gave that regulator. That's why we believe it's physical and
I see. Like the way you soften this tau goes to I infinity is basically coming from that.
Yeah.
Okay. I will believe that.
Yeah, it could be actually. I could say so. One of the parameters we treat it as a free parameter, which we call rho in the regulator. It actually has a special value of 2. When they did it, it could be that not every value of rho is allowed. So
that's true. Remember, I said we generalized it. We don't need the generalization. In fact, everything we plotted for rho equals 2. We did, however, add an extra prefactor which was needed to make the scale duality correct. So, but that should not upset in any way, I don't think, the property that we need to have that you're asking about. So I think everything is fine.
Okay. All right. Thank you. Great talk.
Hi, Keith. Very nice talk. Thank you.
Thank you.
Can I ask a question? So I like very much the model independent approach, but I kind of missed some important ingredient of string theory, which is the dilaton. You actually never mentioned dilaton in your work. And I think there are some old papers by Witten or Waffa that tell us that the cosmological constant in string theory vanishes if the shift symmetry of the dilaton is kind of unbroken. Or can you comment on that?
Sure.
And also the sign of the lambda of the cosmological constant that you're getting.
Okay, we're not getting any sign for anything. We did not. The sign can be anything. And you're asking me questions about things that I worked on 30 years ago. So I can give you a whole story if you want. In fact, it was my doctoral dissertation, the values of cosmological constants in 4-dimensional heterotic strings from the free fermionic construction. This makes sense. I was Henry Tye's student back in the late 80s. But so I was in the hotbed of where the free fermionic construction was being developed at the time. But the point is that the cosmological constant can take any value. usually Planck scale. It can be positive or negative. I even did a landscape study and they were, 73% positive and 27% negative. They can be, so one question that I was interested in at the time, and a lot of people were, this is the late 80s, early 90s, is do you have any ways of getting the partition function, getting the cosmological constant, the one loop cosmological constant to vanish, even with the partition function not vanishing, which is the non-trivial case. SUSY is when the partition function vanishes, so of course the integral of it does too, but the goal here is to have the partition function not be vanishing, but the cosmological constant to vanish. And there were a lot of ideas generated back in the late 80s about this. So you may remember Greg Moore had a paper called Atkin-Lehner symmetry, and he showed that if the string model had an Atkin-Lehner symmetry, then it would not have a vanishing partition function, but it would have a vanishing cosmological constant. Witten had an argument, I guess, that the one you're referring to. I developed something I call generalized Atkin-Lehner symmetry. There was also work later by Kacheru, Kumar, and Silverstein, where they pointed out that if the partition function had theta-1 factors in every sector, but not coming from the same worldsheet fields, then in all sectors, then that construction would not allow a super current to be formulated in the conformal field theory, but yet it would still cause a boson fermion degeneracy. So in that case, they were getting a vanishing partition function, but without a boson fermion degeneracy. And so that was another approach. That was shown later by Tai and Xu not to be true at 2 loops, I think. So, or there was some doubt about it. The answer is people don't know. We still really don't have a good understanding of the value of the cosmological constant and when it can be 0 in the absence of supersymmetry, which is an important question. Non-SUSY strings have dilettante tadpoles that are proportional to the cosmological constant. That's maybe what you meant. And yeah, okay, yeah, that's a classic result, right? The one loop dilettante tadpole is proportional to the cosmological constant just by conformal invariance. And so, therefore, the stability beyond tree level of any non-supersymmetric string is still not understood because we still need to cancel that cosmological constant. Actually, Steve and I had a paper in 2015 in which we pointed out that maybe you don't really care for stability, that the cosmological constant vanish and therefore you have perfect stability. The universe is only so long old, and maybe if we had a very exponentially suppressed cosmological constant, the size of the dilettante tadpole would introduce a small instability which might render the string model metastable, which could be effectively stable on cosmological timescales. That would be good enough. And then we began a whole study, and there's another big paper from us in which we studied how you can build string models which have exponentially suppressed one loop cosmological constants. And then Steve had a follow-up paper with one of his other collaborators in which they extended that to 2 loops. So, there are lots of ideas. It's active research, but we don't know. We're not saying anything about the value of the cosmological constant here. What we are saying is that it is related to the Higgs mass, and we're giving a general result for that.
So is this like a Martin? Is this zero momentum dilaton? Which dilaton are you talking about?
Yeah.
Yeah. Okay. All right.
So, Keith, can you elaborate further on how you relate spacetime and worldsheet regulators, and to what extent this is fixed?
Okay. So let me go back to my slide. I love questions I can answer. This is the basic idea, is that we want to regulate against the divergence. The divergence is going to happen at tau 2 goes, if we choose the fundamental domain, it's going to happen at tau 2 goes to I infinity. Tau 2 goes to infinity. So that is where the divergence is going to be. So we need to regulate worldsheet is fundamental. That's all we care about in string theory. Space-time is derived. So we need a worldsheet regulator, something which is going to suppress contributions to the one-loop integral from the higher regions of the fundamental domain. And so I'm looking for my slide where okay. So anything, don't worry about this direction. That's not tau 1, that's something else. But anything that, here's, if you want, the regulator as a function of tau 2. And as you go towards tau 2 goes to infinity, or equivalently this, it's the same plot, it's going to suppress that part. Okay, so that we know. So it's going to suppress. So let's call there a scale. Let's
Actually,
call...
Sorry to interrupt you, but actually even before this point, this function GA tau 2, can you explain how to relate it to the original? Yeah, you inserted it into the partition function at some point.
Okay, here's all
Yeah.
we do. This is the original amplitude. We insert this, and it is also modular invariant, so we have not disturbed the modular invariance of this theory, but then we demand, okay, here are all the conditions. G must be modular invariant. It should have a straightforward physical interpretation, which we need, and we have. It should suppress the power law divergences at any IR cusp. It should have internal parameters, which I'll get to that in a minute. It should not only suppress the divergences at the cusp, but it should leave the rest of the theory intact as much as possible so that we can still say that it is the same theory that we're talking about. In other words, it should go to 1 anywhere else except near the cusp. And this does that, and here is how you see it. Here is where it's suppressed, but notice it goes to 1. This value height 1 here, it's going to 1. It's a remarkable function. It smoothly just gives you no effect where you don't need a suppression. And then there's a little hump, which we don't understand, but that's modular invariance, I guess required it. And then here is where it does the suppression. So it leaves the theory intact, and then it suppresses the high level. And there's a transition value. So there's going to be a transition value, which is going to be some value t on the worldsheet. Now, how can I ever interpret that in space-time? Well, the point is that whenever you have a t and you're suppressing things above it, then you're saying the contributions of m masses above that are going to be frozen out. These are going to be either, you're basically deciding where you're going to treat this number as 0 and where you're going to treat this number as 1. And so you're saying which states are in the theory, which states are out. So you pick a 1 over t value, and every mass above it is going to be suppressed. This exponential you're going to be treating as killing your divergence. It's not there. It's not contributing. Those states are not contributing anymore. Those are the dangerous ones. And anything lighter, you're saying this number is basically 1, and we're not going to worry about it. So you're effectively defining a scale mu in terms of the masses of the states. Now we're in space-time, for which this is related to t. I think these arguments are airtight. I mean, there's no other way to do this. I mean, if you are really removing certain states from the theory and you're doing it in terms of the quantum numbers, the excitation numbers on the worldsheet, and then you're going to make a mapping that alpha prime m squared is n, then the moment you make that mapping, you are equivalently making the mapping between t and mu in space-time. And then the modular invariance of t goes to 1 over t is going to compel this one. Did I answer your question?
Yes, thank you.
This is not simple.
Yeah, I would need to look into it further to really.
Yeah, no, look, we I think Steve and I and Luca have this attitude that it's all obvious because we've been thinking about it for years, but in reality, every step of this was like pulling teeth. This is what in field theory you would do. You would have a regulator, you introduce a parameter, and from there you get a running scale. We're doing the same thing to the extent that one is allowed to do this. So all of this is about running. This is about constructing an EFT from string theory. But notice, I keep saying, we are spontaneously breaking modular invariance to do that. I kept emphasizing that point. If you don't, and you shouldn't, and you're not trying to make connections to field theory, don't do that. Just say, here's an amplitude, and it diverges or it doesn't, and it has a value. It's only our desire to connect to field theory and talk about running in order to explain things like hierarchy problems to the field theorists that we went down this road.
Well,
that
another way to do it is just to separate the zero mode that will cause divergence, and the fake degrees of freedom guarantees like a modular invariance, right?
Yes and no.
Yeah.
I mean, that's what we said here. You could just separate, as you said, the massless states that cause the divergences.
Yes.
But this truncation of one set of states relative to others breaks the modular invariance so brutally. So
Yeah.
instead, we want to do it smoothly.
No, okay. It will.
But that's
it will
what
break,
we're doing.
It will break the modular invariance, but you can add like some fake thing that will restore that modular invariance.
Well,
and
I
vanish at
think
infinity.
that's
what you're doing essentially.
That's what
right?
we're doing. Exactly.
But like
Because-
my point here is that then like that procedure that's separating and adding out, then you will have a clear string field theoretical understanding that this is going to be some field theory in the space, and you are just separating the zero modes of the action, and the all remain is that the ones that you have the regulator, and that will give you this procedure that is relating the regulators correctly. That should be the way to go about it, rather than just guessing the like how these should matches. Like you once you do this procedure, it will be complete.
Right.
Yeah.
Okay.
At least that's what I think.
Okay, and I don't disagree, but I think we're doing it because
Okay,
if you take t, oh, which way do I go? T goes to infinity. Slide 1 over t goes to 0. Slide this down. The only states that are left that are light are the massless ones.
Yes.
So what you're saying is what we're doing at t goes to 0. But we need to do it in a way that is sensitive to modular symmetry. You're saying, well, introduce the other gunk just as a cloud to make it modular invariant. Well, you know what? This is the other gunk.
Mhm.
So I maintain that what you're doing is exactly right, but that's what we're doing.
Yes. I mean, I would agree with that.
Okay, so good. So this is, again, why T is related to mu. This picture really sort of says it. And I think there's no way to get around that. Yeah, we had to think about regulators. I mean, gosh, in string theory, to think about regulators for space-time scales for running. I mean,
because what I worry about is that the string scale, like, okay, regulators are going to be related, certainly, but the schemes might be different. That the quantity where you compute that you think that you compute in EFT might be different from the like when you compute from the
very good. You're right. There's a
so that's why you have to use string field theory to make that connection exactly. Yeah.
This is not a. Oh, I see now.
Sorry about that.
I see now where you're coming from. String field theory should do all of this in a very natural way.
Yeah.
We don't have a string field theory. Maybe you guys have worked on it and do have one, but we are trying to do this from the first quantized string theory. I mean, second quantized, you understand. We don't have a string field theory. Maybe there is a string field theory where this could come out in a different way. I don't know enough about string field theory. Maybe Steve or Luca do to answer your question. But I think whatever you're going to get out of that has to look like this.
Yeah.
I mean, I would say, so this procedure is very similar to what you do in, well, it's basically the same as what you do in functional renormalization group, renormalization that way.
Yes.
The only difference is that there you put it on momentum modes rather than masses, which basically we're doing masses here. The reason why is, of course, because here we have to be on shell. So then if you're doing string field theory, presumably you can then do something closer to just functional renormalization group, I think.
Okay. All right. I will meditate on these statements. Thank you.
No problem.
Okay, I think we have plenty of questions and discussions. It might be time to thank Keith again for a beautiful talk.
Thank you.
So I'll stop the recording here.